Hi everyone, in this lecture we are going to discuss new topic in module 5, which is related to equilibrium of a planar rigid body. Okay, and in here basically we will talk about equilibrium of a rigid body in a two-dimensional system. Okay, so in module 3, when we talk about equilibrium of a particle, we have formulate two equilibrium equations to restrict the motion of the particle that lay on a two-dimensional plane. So for example, this is the particle and this is the plane. The vertical motion and the horizontal motions of the particle can use to describe all motions of this particle in two-dimensional plane, right? Because the vertical and the horizontal motions are independent to each other, such that the equilibrium equations that we formulate at the times is to say that all forces that are acting on this particle, okay, has to be zero, right? And we further formulate two equations, which is all forces that are acting, all forces in the y directions and all forces in the x direction or horizontal directions is equals to 0. Okay, the same reasoning we will use to formulate the equilibrium equations for two-dimensional rigid body. Okay, so for example, this is a member, a beam, for example. It is rests on a two-dimensional plane right here. Okay, and then the rigid body motions of this member consists of vertical motion, okay, horizontal motions, okay, similar to a particle. However, there is one additional motions that is describe the motion of this member on a two-dimensional plane, which is rotation. Okay, so for a rigid body located on a two-dimensional plane, it has three rigid body motions: vertical, horizontal, and also rotations. Okay, such that the equilibrium equations that we written down, that we will formulate in here, have to say that all forces in the y directions, all forces in the x directions, and also the moment, okay, has to be equal to 0. Okay, then let's start formulate this. Okay, so for general case, okay, there are three equilibrium equations. The first one is sum of the forces in the x direction equal to 0, and then sum of the forces in the y equal to 0, and sum of the moment at any point equal to 0. Okay, and these equations is formulated based on the assumption that the body is located in the xy plane. Okay, with that, we also have learned from module 4 that the moment that we take in here, even though it's take from any point on that plane, it's basically a moment about the z-axis. Okay, and as I said earlier, these three equations are related to three rigid body motion, right, of the structure, okay, in 2D plane. All right, and what are they? So those three rigid body motions are vertical motion, right, translation, in here we use the terms horizontal translation, and rotation. So these are the three rigid body motions of a structure in 2D plane. Okay, so this is the general case for the equilibrium equations. Okay, and then there is some specific case, and I would like to lay it out in here. For example, we have a body, right, structure, for example in here, okay, and let's say we have a line, and the force that is acting on that body are collinear. Okay, what does it mean by collinear? Those forces are acting along the same line of action. Okay, so for this case, if this is line N, then we only can write one equilibrium equation, which is sum of the forces in the n directions equal to 0. Okay. The second specific case in here is what we call as a concurrent forces. Okay, so for example, if I have a body or structure right here, okay, and then I have a point O right there, and I have forces acting on that body, and all of my forces are concurrent at point O. So for example, this is F1, F2, and F3. Okay, for this system of forces, we can write two equilibrium equations. Okay, and if this is the x and y axis, we can write those equations are sum of forces in the x equal to 0 and sum of the forces in the y equal to 0. Okay, and if you see these equations, it's similar to the equilibrium of a particle, right, in 2D plane, right? Right. And then the last one is in the case where all of the forces that are acting on the body or the structures are parallel to each other. Okay, so for example, this is my structure. Okay, and then let's say that this is the line N. Okay, and on this body, all of its forces, okay, are parallel to N. Let's say this is F1N, F2N, and F3N. Okay, in these conditions, there are two equilibrium equations that we can write. The first one is sum of the forces in the n directions equal to 0. Okay, and then sum of the moment at any point equal to 0. Okay, so at any point on this plane is equal to 0. Okay, it could be here, it could be here, it could be here, it could be here, anywhere, and then set it equal to 0. Okay, all right, I think that's it for this lecture, and in the next few lectures we are going to discuss some example problems on how we are going to apply these equilibrium equations that we have described in here. Okay, some important concepts that you need to know from this lecture is that there are three equilibrium equations for a two-dimensional rigid body. Okay, which is sum of the forces in the x, sum of forces in the y equal to 0, and sum of the moment at any point is equal to 0. Okay, and those equilibrium equations are derived based on the fact there are three rigid body motions in two-dimensional plane, which is vertical translation, horizontal translation, and rotation. Okay, since we are able to write three equilibrium equations, so the problems that we solve has to be at most involve three unknowns. Okay, other than that, if we have more than three unknowns, then we have to think deeper whether those problems can be solved with these equilibrium equations or not. Okay, I think that's it for this lecture, and thank you for listening.